Hi, ladies and gentlemen, it's Mr. Green again, and this is another in my series of lessons for AP Statistics, and we're looking at bivariate data. You know, someone brought to my attention the fact that not all data is numerical in nature. So everything that we've been looking at so far has been numerical. What do we do when the data is not numerical? What if it's categorical? Okay? And what we look at in that situation are called two-way tables and marginal data distributions. That's what we're talking about in this particular topic, okay? Bivariate data isn't always numerical. So how do you analyze categorical data? We want to see how two things relate to each other, okay? We can't always do a regression on categories. We use two-way tables, okay? What's a two-way table? A two-way table combines two categorical variables into one table. So we can observe any sort of relationship between them. It's made up of rows and columns for each type of category. Okay, let's be honest. It's just a spreadsheet. That's all it really is. Do not take it as anything more than that, okay? It's just a spreadsheet. So if I took a survey of 4,826 randomly selected young adults aged 19 to 25 and asked, what do you think the chances of you will have much more than a middle class income at age 30? We're just asking their opinion, right? We don't have numerical data. It's something we could only express it as, the counts. We could say, well, the people who said almost no chance, well, there are 194 of them, and 96 of them were male, 98 of them were male, 96 of them were female. Some chance, but probably not. Well, 286 of them were men, and 426 were women. A 50-50 chance, 720 men and 696 women. Can you see where I'm getting that data? I mean, but the question becomes, what is this telling us? Well, you know what? We can start to express and look at each of the distributions, look at the distributions of each variability separately. These are called marginal distributions. The distribution of values of that variable among all the individuals described in the table. So let's look at this. If I was looking at how many people said no chance at all, I would take 194 and divide it by 4,826. And that would give me 4%. Okay? So 4% of the people responded saying there was almost no chance. Okay? Well, what about how many people responded were female? I would take this total right here, 2367, and divide it by the 4,826, and I would get 49%. 49% of the people that responded were female. Now, I can almost predict that this is going to be 51%. I haven't done that math yet, but if we take 2459 and divide it by 4826, helps if I push the right numbers on my calculator, I get 50.9 or 51%. That seems pretty obvious, Mr. Green. Well, marginal distributions don't always give us enough information. What if we wanted to analyze the relationship between two variables? For example, what if we wanted to ask the question, is a young man more likely to think he's going to be rich by 30 than a young woman? Then we have to look at conditional distributions. This describes the values that the variable among the individuals who have a specific value of another variable. These are separate conditional distributions for each value of the other variable. So, in other words, if we're looking at this table, these are what I was calling marginal distributions, these that were out here in this column, or these that are down here in this column. Those are marginal distributions because they're in the margins here. But if I'm looking at this distribution right here, that 4%, what would I be doing? I would be taking this 96 and dividing it by the total number of females, 2367. And that gave me the number of females that thought there was absolutely almost no chance. I would do the same thing for the men, 98 divided by 2559, and that would tell me the percentage of men that thought there was almost no chance. What's the percentage of men almost certain they'll be rich by age 30? I would take this 597 divided by 2459, and I would get 24%. Okay? Well, we could do the same thing for the women there too, couldn't we? We could take 486 divided by 2367, and we would get 21%. Can we compare those percentages? Sure. That's part of conditional distributions. During the calculation for all the entries in a column, it gives the conditional distribution for that column variable. This distribution describes only young adults who meet the condition that they were either male or they were female. Conditional variable, the total variable. Conditioning variable, the total variable. So, conditional distributions. Note there are two sets of conditional distributions for any two-way table. We looked at the conditional distributions for the two genders. We could also have looked at the conditional distributions of genders for each opinion. What are you saying, Mr. Green? Well, I could have taken this 486 and divided it by 1083. Right? That would have told me what percentage of the people who thought they were going to be rich were female. Depends upon how you say it, doesn't it? Or what percentage of people who thought they were almost certain they were going to be rich by age 30 were male? Depends upon how you say it and how you want to do. So how do you know which conditional distribution to calculate? By rows or by columns? It depends upon the question you want to answer. Think about whether the changes in one variable might help explain changes in the other. In this case, it seems reasonable to think that gender might influence young adults' opinions about their chances of getting rich. To see whether the data supports this idea, we should compare the conditional distributions of opinions for women versus men. Okay? So what we'd do there would be the row calculation. The column calculations there. Okay? So do the opinions differ between men and women? Well, let's see here. Women are a little less positive here that they're going to be rich. Okay? They're less likely to select these two upper columns. But they're pretty much consistent down here in the lower columns. So it just depends upon how you're looking at it. Now, I'm not trying to give you the answer to this. I'm just trying to show you how it's done and how you calculate it. Okay? So, another example. Accident victims are sometimes taken by helicopter from an accident scene to a hospital. Helicopters save time. Do they also save lives? That's the question. Let's compare the percentage of accident victims who die with helicopter evacuations with the usual transport to a hospital by road. There are hypothetical data and illustrates a practical difficulty. It is not actual data, so don't worry about this, okay? So here we've got this information. I got 64 people died, and I've got 136 survived. And over here I've got 260 and 840. So if we do a little bit of calculating the percentages here, they're saying discouraging. Why are they saying discouraging? That's 32%, and this one is 63%, 68%. But this one over here, 26 divided by 110 is 24%. Okay. And 840 divided by 110 is 76%. Wow. Wait a second. That doesn't look quite right. More people died percentage-wise going via helicopter than went via road. More people survived going by road than going by helicopter percentage-wise. What? That's why they're saying here, this seems a little discouraging. Do you think there's any other explanation for this information? Well, one thing that comes to mind that you might keep aware of is that they don't always call the helicopter. If it's a minor accident, minor wreck, they're going to send them on the road, right? It's only the major ones that they call in the helicopters to pick them up. Okay? So, what if we divided the data based upon the seriousness of the accident? So let's look at the seriousness of the accident and the number of people who died and survived. Well, this is 48, and this is 52, and this is 60, and this is 40. Well, very serious accidents, it's pretty obvious. 52% survived versus 40% survival. I want to be in that helicopter if it's a very serious accident, don't you? And as far as deaths are concerned, 60% died if they went over the road, but only 48% died if they went via helicopter. Give me that helicopter, man. If it's a serious accident, I want that helicopter. But let's look at the less serious one over here. We get 16% died and 84% survived. That's pretty good. And we divide this out with, wait a second, there's a missing zero here. That's 1,000. This is 80% survived and 20% die. You know what? These don't look that different, do they? A less serious accident, 16% died via helicopter and 20% died via road. That's not that big a difference. And 84% survived and 80% survived. You know what? I'm seeing that this one has a higher survival rate via the accident, via the helicopter. But this one, it's a slightly higher, but it's not as big a higher. You know what? I'm still saying if it's a serious accident, give me that helicopter every time, right? This is called Simpson's paradox. How can it happen that the helicopter does better for both of the groups of victims, but worse when the victims are all lumped together? Let's go back and look at that real quickly. Okay? Here we've got them lumped all together, and the helicopter did terrible. I mean, 32 and 68 versus 24 and 76. It's worse. Yet when we broke it up into two different groups, it's pretty obvious the helicopter wins over here, and it's kind of less obvious here, but the helicopter still seems to have a little bit higher survival rate. Still want to be in that helicopter, don't you? But the point there is, if you examine the data closer, half of the helicopter transport patients from serious accidents compared only with 100 of the 1,100 road transport victims. So the helicopter carried patients who were more likely to die in the first place. The seriousness of the accident was a lurking variable that hid the true relationship between the survival mode of the transport to a hospital. Simpson's paradox states that an application between two variables that holds for each individual value to a third variable can be changed or even reversed when the data for all the values on the third variable are combined. So that lurking variable can make your data actually do opposite what you think it should do if it's not excluded out. Lurking variables are a variable that isn't actually visible in the table data, but it strongly affects the data. The likelihood of dying in the first place is the lurking variable here in this particular one. Confounding variables, we say that two variables x and z are confounded when we can't isolate their separate effects on the response variable, y. Both may have an effect on y, or perhaps only one does, but their effects are confused and confounded with one another, so we don't measure both x and z. The variable z is a lurking variable in this case, and it has an effect that we can see, but we can't tell where the effect really comes from, x or from somewhere else. Okay? The common response? The common response occurs when changes in an explanatory variable x and a response variable y are both driven by a lurking variable z. Okay? Now, what I'm telling you here is make certain you understand some of this information. Read the study guide real closely for this unit. Okay? Make sure to thoroughly read that study guide and understand what's going on there before you get into that 3.6 quiz. It's going to be important for you to make certain you do that. Okay? Having said that, lots of courses. Make certain you're sending me that you're in AP Stats when you send me questions. I'm available in Toga if you need my assistance. Come on by. I want to help you as much as I possibly can. And I'll look for you in Class Connect on Thursdays. Otherwise, I'll see you next time we get together. Bye.